Hello and welcome back to Multidimensional Integration, the video series where we talk a lot about the n-dimensional Lebesgue measure and the Lebesgue integral. And in today's part 18, we continue what we have started in the last video and show the completeness of the L-infinity space. So we can say that the essentially bounded measurable functions on Rn form a Banach space. However, as always, before we formulate the proof of that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a member on Patreon or Steady, you can download the additional material with the link in the description. Okay, then let's immediately start by recalling that L-infinity with a curved L stands for the essentially bounded functions. And then usually we use the straight L-infinity to denote the space of equivalence classes. And the important part you should remember here is that two functions f and g are equivalent if and only if they coincide almost everywhere. This means that the exception set where we don't have the inequality has Lebesgue measure 0. And now the good thing is that on the straight L-infinity we have a well-defined norm. Hence what we actually have inside the norm symbol is a whole equivalence class. And I can already tell you, later on we will just omit mentioning this equivalence class symbol altogether. But for the context of this video here, it makes sense to explicitly write it down. And now in order to define the infinity norm, we can just take a member from the equivalence class and look at the essential supremum. This means we look at the infimum over all possible upper bounds C, but we can omit a measurable set A. And now the catch is that this set A should have Lebesgue measure 0, which means that our C here is an essential bound for f. And because of this definition here for the infinity norm, you see it does not matter which member from the equivalence class we actually choose. A possible difference can only happen at a set with Lebesgue measure 0 anyway. Okay, by having these definitions, it's easy to check that we have a well-defined vector space with a well-defined norm on it. And now with respect to this given infinity norm, L-infinity is a complete normed vector space. So this is what we call a Banach space, and you should know this means that every Cauchy sequence in the space is actually a convergent sequence. And this is exactly the statement we want to prove here. So the starting point is simply that we take a Cauchy sequence in L-infinity, which means we have a whole sequence of equivalence classes. And this also means that we can just take a representative from each equivalence class and we call it Fn. Therefore our Cauchy sequence looks like that. So you see, the important part here is that you actually know what the term Cauchy sequence actually means. This is not so hard. Roughly speaking, we can make the distance between two members as small as we want. And now let's say we want to make it smaller than 1 over k. This means that we can find a starting index that we can call capital N, and after that the distance is smaller than 1 over k. And maybe as a reminder, because this capital K depends on k, we put it into the index. And now it's quite simple, we just consider any two indices n and m, and there the distance is smaller than 1 over k. And to be precise, we have the equivalence class of Fn minus the equivalence class of Fm. And this distance we measure with respect to the L-infinity norm. And we want to have it smaller than 1 over k. And at this point you already know that we can also have this inequality pointwisely if we exclude a set with measure 0. So let's formulate this for our given k. So for the index k and the two indices n and m, we find a measurable set A. And to make this clear, let's call it AKNM. And now you know, outside of this set, we have the inequality pointwisely. So we have Fn of x minus Fm of x measured in the absolute value. And by the definition of the infinity norm, this one is definitely less than or equal to 1 over k. We don't need the strict inequality, so I just use what we have here in the definition. So moreover, we have it for all points x in Rn with the exception of our set A. And now we have an important insight here. We have countably many sets with measure 0. Therefore, we can easily look at the whole union of these sets. So for example, we can go over all possibilities for the indices n and m. And we know these indices have to be greater than or equal to nk. And in addition, we can also form the union over all possible k's. So not a big problem, the whole thing is still a countable union. And since we have the sigma additivity for the Lebesgue measure, we know that the resulting set here is still a set with measure 0. And maybe to keep it simple, let's call this set B. And this is quite nice because it allows us to use the set B as the exception set in this inequality as well. And if you combine that with the first sentence that we have here, we see that we have a Cauchy sequence in C. So maybe let's quickly formulate this as an intermediate result. So you could simply say the inequality holds almost everywhere. And by the definition of a Cauchy sequence, we immediately see that we have one here for every point x. So our fnx is a nice Cauchy sequence in the complex numbers. And since the complex numbers are complete, we know that this sequence is convergent. In other words, we have a pointwise limit for fn. Hence the limit n to infinity of fnx exists and it's a complex number. And obviously this is what we can use to define our limit function. And it makes sense to call this limit function just f. And we can already define it almost everywhere because only the points in the set B make problems. And indeed there it does not matter what we do, we can just set the function to 0 for points in B. And now the idea is to use the same inequality as before and just pull the limit in to get the function f of x. So for example, we can just say that we have the limit m to infinity and then we push it in and then we have this inequality for our limit function f. Of course, the whole thing also implies that if we go to the supremum, then this one is also less or equal 1 over k. So this is nothing special, it's just reformulating the same thing. However, here we might add that the whole thing holds for every index n greater than the index nk. So in particular, we can also form the limit n to infinity and we still have the inequality. However, since k was arbitrarily chosen at the beginning, we know that the inequality has to hold for every k. Hence, the only possibility for the limit is that it is already equal to 0. Therefore, it's actually allowed to say that we have a uniform convergence of the sequence of functions outside of the set B. Moreover, what we also get is the convergence with respect to our L infinity norm. Clearly, the norm of these equivalence classes here cannot be bigger than that supremum, which means we also are at 0 in the limit. Hence, the only thing that remains to show is that f is also essentially bounded, which means that this equivalence class also lies in L infinity. And then we finally have that the chosen Cauchy sequence is convergent in L infinity. And in order to show that f is essentially bounded, we don't have to do much. We can just use that every fn in the Cauchy sequence is already essentially bounded. So we know that there is a capital Cn for the function fn. And in addition, we also find the corresponding set an with measure 0. And then what we have is that fn of x is bounded by Cn outside of an. And at this point you might already guess that we can simply combine an with the set B from before and we still have a measurable set with measure 0. And now we can just show that outside of this set our new function f is bounded. And indeed, this is just the triangle inequality for the absolute value. So we have f of x in the absolute value, and now artificially we add fn of x. And then by using the triangle inequality, we get out two terms. And for the second term, we already know that we have our constant Cn. And moreover, the first term we also already know, because this one is always less than or equal to 1 over k. Hence, in total, we also have a bound for f of x. So for example, to make it simple, we can just take it as Cn plus 1. How large the bound is not important, it's just crucial that we have one. Because that means that f is essentially bounded, so it lies in L infinity. And then this tells us that the equivalence class is exactly the limit of our given Cauchy sequence. So in summary, the nice result that we get is that any Cauchy sequence in L infinity converges in L infinity. It has a limit in the same space, and this makes the space complete. And there you have it, this is the whole proof of the completeness of L infinity. And now I guess you also want to see the proof for the completeness of the other LP spaces. Indeed, it works similarly but also differently, because for the norm in LP, we have to bring in the integrals again. Therefore, this is definitely something we should discuss in a separate video. So I really hope I meet you there again, and have a nice day. Bye bye.